You remember that we have done this harmonic oscillator, simple harmonic oscillator using the solution of Schrodinger equation for these half kx square, which was written as half m omega square x square kind of potential. And then it involved a lot of variable transforms and finally getting the solution in terms of these Hermite polynomials. And what we got as this, the energy has a particularly simple form, and which is h n plus half h cross omega, where n can take values 0, 1, 2 and so on. So, even at n equal to 0, you still have an energy which is called as the 0 point energy. And that was a sort of algebraic solution of this problem, where the Schrodinger equation was solved for these potential. There is a simpler way of doing it, and let us review that. And so that's why it's written as harmonic oscillator revisited, and we'll revisit it in terms of some notations called as the raising and lowering operators, which are written as the raising operator is written as a dagger and the lowering is written as a. And these operators are will be helpful in writing down the Hamiltonian, and also will be helpful in writing down the wave functions corresponding to this Hamiltonian, which already you know, but there is a much simpler way of arriving at things. And then we will define a number operator in terms of a and a dagger, and we will review some of the commutation relations which are helpful in this regard. And then finally, we will be building up the eigenstates of the Hamiltonian. All right. So, what we have is that, just to remind you, that this is the simple harmonic oscillator Hamiltonian. So, we have a p square over 2m plus a half m omega square x square. The notations are standard. So, p is the momentum, m is the mass, and x is the displacement from the equilibrium position. And this is the Hamiltonian that we had to solve, and we did that. Just to remind you of these essential commutation relations, this is equal to I h cross, and so this has to be satisfied by these p and x operators. So, they cannot be simultaneously determined, and the reason that the commutation relation is non-zero, because these are infinite dimensional vectors. So, just to give you a short introduction of these a and a dagger operator. Before that, let me write down these things in terms of the a and a dagger operator. So, what we do is that we make some dimensionless variables, where x tilde is nothing but root over m omega by h cross. Omega is the angular frequency, and x, and we have p tilde, that is a new variable and is a dimensionless variable, is equal to p divided by root over m omega h cross. Okay. So, these are the two relations that we have, or rather dimensionless variables that we want to work with. It's exactly same as the p and x, excepting that we have rendered them so dimensionless variable. They are still variable, but they are dimensionless. And instead of this I h cross x tilde p tilde, they obey the commutation relation which is given by I. Okay. And nicely we can write down the Hamiltonian, that is again a dimensionless Hamiltonian, which is nothing but half p tilde square plus x tilde square. And this is a very nice form, or rather very convenient form, because both these variables that we see there, they are quadratic, and there is no other factor there apart from this half. And the way we can do it is that we can write down this h tilde, which is equal to h by h cross omega, and that is equal to p square over 2 m h cross omega plus half m omega square x square divided by h cross omega. And so, your E n tilde, which is eigenvalues of this Hamiltonian, would come out as simply n plus half without any dimension of energy, which is h cross omega associated with it. So, we have x tilde, p tilde and h tilde, all are dimensionless operators. This makes the algebra easy. There was no other reason for introducing that. So, your h tilde acting on all these wave functions will give us E n tilde returning you back the wave functions, where E n tilde is what we have just written there. Okay. So, just makes the life a little easy, and there is one short word of caution is that your h tilde is equal to, as you saw, that it's equal to x square plus p square, or p square plus x square is the same thing, but this is certainly not equal to half of x tilde plus I p and x tilde minus I p tilde. Okay. And this is true because your x tilde and p tilde, the commutation is not equal to 0 and it's equal to I, which is what we have said. Okay. Now, we introduce these operators, these raising and lowering operators. So, let us call them as lowering and raising operators, and in some books they call it a Dirac notation. They mean the same thing. So, your A operator is 1 by root 2 x tilde plus I p tilde. Say, had you not made this x tilde and p tilde, you will have to carry around this m h cross omega, etc. So, this looks simpler at least, and A dagger, this is equal to 1 by root 2 x tilde minus I p tilde. And I stopped short of explaining what is A and A dagger. So, A is a vector, in general a vector with some entries like this. So, it is like A0, A1, A2 and all the way up to AN, and A dagger is basically a row vector with all this A0 star, A1 star, A2 star and so on till AN star. Okay. So, what you do in dagger is that, just like any matrix, when you take a dagger, you take a transpose and the conjugate, and this is exactly what you do there. So, this A and A dagger have these forms, and you can do a sort of reverse transform, or rather write this x tilde and p tilde in terms of A and A dagger, which are going to be useful for us. So, it is x tilde equal to 1 by root 2 A plus A dagger, and p tilde is equal to 1 by root 2 A minus, or rather this is, let us write this dagger first. So, this will be A dagger minus A, and this A dagger plus A for x tilde, and p is equal to 1 by root 2 A dagger minus A. So, we are going to use these operators to solve this problem of quantum harmonic oscillator, and though it looks like that these ladder operators, or these are sometimes called as ladder operators, these raising and lowering operators that you see are particularly important, because I am just a priori telling you this, that we have n equal to 0 and then n equal to 1 and then n equal to 2 and then n equal to 3. These are the energy levels of the harmonic oscillator. This is h cross omega, this is h cross omega, this is h cross omega. This is of course well known. But if you think in terms of these indices, this looks like that this small n equal to 1 or small n equal to 0 here, small n equal to 1 here, n equal to 2 here and 3 here, they correspond to oscillators, because suppose this has no oscillator, so its energy is half h cross omega, and this has one oscillator, it's 3 half h cross omega, and then it's 5 half h cross omega, and so on. So these are the energies of these things, and it looks like that these n actually denotes the number of oscillators that you have. Each oscillator will have an energy equal to half h cross omega, and then you can just simply build up all these states by assuming that these are occupied by 3 oscillators and 4 oscillators and 5 oscillators and so on, and their energies will be given by this n plus half h cross omega, where n is this number that we are talking about. So this n really has to be equated, or rather there has to be a correspondence between n and the number operator, and that's most simply comes out from this analysis that we are talking about. So let's look at with these as the backbone of this formalism, which is truly sort of parallel formalism to the algebraic method that one can do, which we have done it sketchily. We haven't done it very elaborately, but it can be done. It is in the interest of keeping the mathematics a little brief, and also to emphasize on the main results. We have cut down on the solving the differential equation and all those variable transforms, but nevertheless we got the answers which are for the eigenstates and the eigenenergies. We are going to get the same thing here as well. Okay. So what kind of operators are these A and A dagger? Are they commuting with each other, or they are non-commuting? What kind of eigenstates do they have? Are they the eigenstates of these n operator that we are going to talk about, and so on. So these are some of the questions that we are going to ask, and it would correspond to the commutation relations, or rather they would be given by the commutation relations. So let's see this commutation relation A and A dagger, and this is equal to half, and then we have a x tilde plus I p tilde comma. So this is that the first term, which is A, and so this is x tilde minus I p tilde and this commutation. So x will of course commute with x and p will commute with p, but what will not commute is that x will not commute with p or p will not commute with x. So we will have two terms which are non-zero, which are p tilde x tilde and minus I by 2 x tilde p tilde. So these are the cross terms that don't commute, and this is equal to minus I h cross and this is equal to plus I h cross. So that gives us I by 2 into minus I h cross and minus I by 2 into I h cross. So this minus I square becomes equal to 1. And this is equal to, so sorry, I will use this as simply equal to, because x and p commutation is not I h cross, but it's simply equal to I, which is what we have said. So this h cross will not be there in the in this operators. So this is equal to half and this is equal to minus of minus half. So this is equal to half as well. So this is equal to 1. So A and A dagger do not commute. And their commutation relation is 1, just like p and x do not commute, but now the commutation relation is not like x and p, but non-zero, but it's equal to 1. Okay. So let us see an important quantity called as A dagger A and see if it is something meaningful. And a priori telling you that this quantity is nothing going to be nothing but the number operator, which when acts on a given state will count the number of oscillators that are there in the state. So, so this is going to be an important quantity in our discussion. So, it is x minus I p into x plus I p, all these with a tilde and so on. So, this is equal to half x tilde square plus p tilde square plus I x tilde p tilde, and one has this as, so now this is known to be equal to So, this is equal to I, and so this is minus, so this A, this is nothing but equal to minus 1, and so this is equal to half x tilde square plus p tilde square minus 1. Okay. And if you remember that half of x tilde square plus p tilde square is nothing but the Hamiltonian, which is what we have written down earlier. So, this h tilde is equal to a dagger a plus half, or it is also equal to a dagger minus half. Okay. And that gives you, because you can show that because you have a dagger equal to 1. So, a dagger minus a dagger a equal to 1. So, if you want to interchange, then you have to have a minus coming in. So, what I did was that a dagger a was replaced by a dagger. So, a dagger a is equal to a dagger minus 1, and that makes it a dagger minus half. So, that is the Hamiltonian in terms of these raising and lowering operators, and we are talking about not the bare Hamiltonian that we have started with, but we are talking about a dimensionless Hamiltonian whose eigenvalues are the dimensionless energies. Okay. So, if we return back to the Hamiltonian that we had started with, then it is a dagger a plus half h cross omega. That immediately tells us that this quantity, which is a dagger a, is nothing but the number operator. So, this is the number operator corresponding to, so n is the number operator, and written in terms of these a and a dagger as equal to a dagger a. Okay. And so, let us see what is this property of n. Now, H is of course Hermitian, so n has to be Hermitian. So, let us see that n is a Hermitian operator. And how we can show this is that we have n dagger, which is with n equal to a dagger a, and n dagger is a dagger a dagger. Now, when you do that, what you have to do is that a b dagger is equal to b dagger a dagger, and that can be easily proved. You can take any two Hermitian matrices, and then that you can just multiply, or you can use it a basis to show that when you take a dagger or a transpose, you have to take it from the opposite direction. So, this tells you that this dagger is equal to a dagger a, which is equal to n. Now, that means that n dagger is equal to n. So, this is the Hermitian property, right. So, it is a Hermitian operator, and so the eigenvalues are real and physical observables, and so your h dagger becomes nothing but almost equal to n accepting a factor of half. So, that dimensionless Hamiltonian is just n plus half, and we are now very sure that the eigenvectors of h tilde and n are same. Okay. And you know that because h tilde n is equal to 0. Okay. And which is easily seen from here, because n will commute with n and half is just a number. So, n will h tilde will commute with n, and if that happens, then eigenvectors of h and n are same, and of course, vice versa. Just a quick check, because we need this for a later use. So, some of the commutation relations that we have been talking about. So, what is the relation, commutation relation with n a, and that is equal to a dagger a and a, which is equal to a dagger a and plus A dagger A A. Okay. So, I have just used this A B C, it's equal to A B C plus A C B. Okay. So, that is what I have used, and this is of course equal to 0 because A commutes with A, and A dagger A is equal to minus 1, and so this is equal to minus A. Okay. So, the commutation relation between N and A are not same, or rather not 0, and because they are not 0, the eigenfunctions of N and eigenfunctions of A are different. So, the eigenstates of N are not the eigenstates of A or A dagger. Let me also show this the same thing for A dagger. So, A dagger is equal to A dagger A dagger, and we have this as A dagger A dagger plus A dagger A dagger A. Okay. This is certainly equal to 0, and this is equal to 1. So, that gives you A dagger. So, the commutation relations of N, the number operator that we have identified, or we have called that as A dagger A. So, A dagger A and A, they do not commute. In fact, the commutation relation gives something finite, which is minus A, and N also does not commute with A dagger and gives you just A dagger. Okay. So, these two are important. Let me write that. So, N A is equal to minus A, and N A dagger equal to simply A dagger. These are important relations for us. Okay. So, let us see some little more properties of this. So, the first property of these various operators and their the eigenstates. So, the eigenvalues of N let us call them as N, small n. Okay. They are positive or 0. Okay. They can be 0, but they are positive. And how do we do that? Let us see this A acting on some state, okay, psi n, and the square of that. So, what we do is that if we take this state and take the norm of this vector. So, this is a vector because there is an operator that is acting on the state. So, it is a vector, and what we do is that we take this A psi n, that is a norm of the vector, and call this norm of the vector, of course, it is a length, and this length has to be greater than 0 or equal to 0 at the most if there is no for a null vector. Okay. So, this thing can be written as this mod square is psi n A dagger A psi n, this is greater than equal to 0. Okay. So, that tells us that psi n n psi n is greater than equal to 0. So, I think it is clear that A psi n mod square is like a psi n, okay, and the conjugate of that. So, that will be a bra psi n and a dagger, and that is why we have written that. Okay. So, this means that these expectation value of n between these states, psi n states are greater than 0, which tells you that if we have a relation where n acting on psi n gives you, it is an eigen value equation, that is psi n's are the eigenstates of this capital N operator, yielding you the eigenvalue which is small n and returns you the eigenfunction this psi n. Then we have these from this, it is clear that this n has to be greater than equal to 0. So, that tells you that the eigenvalues of n are a positive definite, or they could be 0 in the worst case, or rather in some special cases when n equal to 0. Okay. So, now, so n equal to 0 state. So, how do we sort of the n equal to 0 state, how do we characterize that, or how do we understand that? So, let me, what I do is that let me sort of for an arbitrary state phi, let us say this is equal to 0. Okay. This phi is arbitrary. So, if we take the a dagger a, that is left multiplied by this equation, this is equal to 0 as well. So, which means that n acting on phi gives you 0. Okay. So, the eigenvalue of these operator of n on phi is equal to 0. Okay. So, which tells you that this is this phi, now let us say we call it as a psi 0, because we are writing psi n, and this is the ground state of the system, and the ground state has no oscillators, and the energy of this state is equal to half h cross omega. Okay. So, what we have proved is that there is a n equal to 0 state, which is also special. It contains no oscillators, but it has certain energy which is equal to half h cross omega. And the way we prove that is that we take an arbitrary ket and apply the a operator, which is a lowering operator, on this state, and then suppose this relationship exists, and then we left multiply it or left operate it by this a dagger. So, a dagger a on phi will be 0, a dagger a is nothing but n, and that tells you that the eigenvalue of these state, that is operation of n on this particular state, is 0, and let us call that state as the ground state of the system, and which has no oscillators. Okay. So, then let us also do this number 3, property number 3. If n is greater than 0, then the vector a psi n is a non-zero vector of non-zero eigenvector of n with eigenvalue n minus 1. This really justifies the name that we have given it to is a lowering operator. So, which means that suppose we take an n for which it is n is greater than 0, because for n equal to 0 what happens we just saw, but for any other n which is larger than 0, if a acts on that state or that eigenstate, I mean that eigenstate of n, what it will do is that it will reduce the eigenvalue by n minus 1, and that will not be an eigenvalue equation. So, a acting on psi n will not give you n minus 1 psi n minus 1, okay, or rather psi n. So, this is untrue. What I am saying is that a psi n is not equal to n minus 1 psi n, and the reason is that this is wrong, because psi n's are not eigenstates of a, and the reason is for that is that capital N does not commute with either a or a dagger. So, this psi n which are eigenstates of n are not eigenstates of either of a or a dagger. So, let us see how we can show this. Or so, n a, that is a commutator acting on this psi n, we have found out that the commutator is minus a psi n. So, we can open this bracket, and we can write it as n a psi n. N a means the number operator multiplied by the lowering operator, equal to a n, that is the other term. So, I have taken it on the other side, a n psi n and a minus a psi n. And what we can do is that we can because n acting on psi n will give me a n psi n, and this will return a psi n. I mean, return means this will not be. So, let me erase this, because this you know. And so, this is true. So, this a psi n. So, this is equal to n minus 1 a psi n. So, this is exactly what we are saying, that n acting on a psi n, it gives you and so n acting on this state will give us this n minus 1 lowering of these oscillators, the number of oscillators, and returns me these returns us this a psi n. Okay. So, that tells you that a psi n is an eigenvector of n with eigenvalue equal to n minus 1. Okay. That is an important thing. Similarly, for the other one, that is again for n greater than 0. So, a dagger psi n is an eigenvector of n with eigenvalue n plus 1. Okay. And how you can show that is that it is exactly in the same spirit. You take this n a dagger, and once you do that, it becomes equal to a dagger psi n, and then open up the bracket again, and what you have is that n a dagger psi n. So, n a dagger psi n, and this is equal to n plus 1 a dagger psi n. So, it is the same relation that you have for a. So, a dagger psi n is an eigenvector of n, returns the eigenvalue n plus 1, and returns me the same ket. Okay. So, we have acquired a lot of properties of this. So, let us see the the properties of these eigenstates of the Hamiltonian. So, we know that A acting on the ground state will give me 0. So, apart from this raising and lowering, they are also called as a creation and annihilation operator, which is probably a more sort of contextual thing in this particular context, because a dagger creates an oscillator in a given state and then takes the state to the next available, the next higher state, and A destroys or annihilates an oscillator and then brings the system from one higher state to a lower state. So, there is no destruction or annihilation possible in the ground state, because that corresponds to n equal to 0, which means the number of oscillators equal to 0. So, you are left with A psi 0 equal to 0, and a psi 1 is simply equal to a C 1, A dagger, and a psi 0. Okay. So, what I did is that here I wrote down a coefficient. So, C is an unknown coefficient. At this point, we have to find that using normalization. But what is important here is that the first excited state, or the state, so n equal to 0 is the ground state, and we are trying to see that how can we get the first excited state. So, what you do is that you create one oscillator in this state by using a dagger, and then you go to the psi 1 state, the first excited state, and this is exactly what we have done. Now this has to be normalized, and so this is the normalization constant, and it has to be found out from normalization. Let's see how we can do that. So we can do this normalization as psi 1, which is equal to a C mod square, and then we have these psi 0, and we have a dagger psi 0. Now a dagger is nothing but C1 square psi 0. So this is a dagger a plus 1. This is from the relation that we have written down earlier, that a dagger is equal to, so this is the one that we can change this order. So when you go from a dagger to a dagger a, you simply pick up a plus sign. We have written that somewhere here. So this is equal to psi 0, and so this is nothing but equal to C1 mod square and a psi 0 a dagger a psi 0 and psi 0, assuming everything to be normalized. This is equal to 1, and this is nothing but equal to 0, because a dagger is a number operator that when acts on the ground state gives you 0. So we have this is equal to, and the left hand side equal to 1 as well. So 1 equal to C1 mod square into 1, that tells us that C1 is equal to 1. Okay. So what we get is the first excited state of this system to be equal to a dagger psi 0. So we are given the ground state, and then we are trying to successively build the eigenstates of the Hamiltonian. So the first excited state you build up from the ground state by once operating the creation operator or the raising operator. How do we do the next one, the second excited state, which is so let's have this picture in mind all the time. So this is n equal to 0, n equal to 1, n equal to 2. They are all equidistant from each other in terms of energy. So we want a psi 2 which is equal to a C2, and we have to have a dagger and then a psi 1, right? And we again do this psi 2, that normalization gives you a C2 square, and this is equal to a psi 1 a dagger psi 1, and again I change that C2 mod square is equal to a psi 1 a dagger a plus 1, and then you have a psi 1 there. So now we have this C2 mod square, and we have two terms. One is psi 1 a dagger a. So this is a psi 1 plus psi 1 psi 1. Okay. This is normalized, and the left hand side is equal to 1, and this is nothing but 1 because n acting on psi 1 gives me these 1 and psi 1. So when you take an overlap with psi 1, it gives you 1. So this is equal to C2 square, and we have 1 plus 1. So that gives you C2 is equal to 1 by root 2. So my psi 2 comes out as 1 by root 2 a dagger psi 1, and that will be 1 by root 2, and if I do it twice, I can generate this psi 2 state if I do it twice on the ground state. Okay. So that tells you that psi 2 dagger can be generated from the psi 0 by with these these kind of normalization and A dagger square. And so we successively, so when we are the ground state and we want to go to the second excited state, we have to create two oscillators, which means that we successively operate the ground state by these A dagger twice. Okay. So similarly, an nth eigenfunction of this oscillator can be written as psi n. So this is, you know, similarly, or you can say that by induction. So this is C n and A dagger, and it's on psi n minus 1, and so this is equal to psi n, and this is C n mod square psi n minus 1 A dagger A plus 1 psi n minus 1, and so on. And then again I calculate this A dagger A acting on psi n minus 1 will give me n minus 1, and this will be like C n mod square, and then we have this psi n minus 1 n psi n minus 1 and plus psi n minus 1 psi n minus 1. Okay. So this will give me n minus 1. So this is like a C n square, and then there is a n minus 1 plus 1. So this is equal to this whole thing is equal to 1. So C n is equal to, so this will cancel, and this is like 1 by root n. So a psi n, that is an nth arbitrary n, for an arbitrary n, the nth eigenstate can be generated from the ground state by successively operating the creation operator that many times. Okay. So this is like 1 by root n and A dagger to the power n and psi of n. I mean, here of course we have these, we'll write this as A dagger and acting on psi n minus 1, and so this can be written as 1 by root n, and we'll have n minus 1, and then we have A dagger square. Well, I should not write it here, it should still be n A dagger square, and then we have also a root over n minus 1, and then we have a psi n minus 2. So if you want it to be from the psi 0, so psi n can be generated from the the ground state as psi 0, psi 0, and you operate it by A dagger to the power n times. So A dagger operated on n times on this psi 0 will produce the nth eigenstate of the problem, and you see a 1 by n factorial, because if you collect all these root over n, n minus 1, n minus 2, etc., that will give you the 1 by root over n factorial, which comes as the this normalization constant. Okay. And of course, these are normalized, the psi n's, each of the psi n's are normalized, and so on. So we have the psi n and psi n m, and this is equal to delta n m, and each one of them is normalized, we know, and this psi n, the outer product is equal to 1. Okay. So this is in a nutshell what we wanted to discuss. Let me see a little more properties of this A and A dagger, which will help you to appreciate these ongoing discussion more. So these application of A and A dagger. And what we do is that we'll simply show that let me write down this result first, and then we'll show this. So n plus 1 psi n plus 1. So, even if its psi n is not an eigenstate of A dagger, it still gives you a relation which is known to us. A psi n is equal to root over n psi n minus 1. So, A or A dagger acting on the eigenstates of n, that is psi n, changes the state and gives you an eigenvalue which is not eigenvalue, rather that gives you a coefficient which depends on n. Okay, because I can't call it an eigenvalue equation because it is not returning me back the state, it is giving me some other states. So, the coefficient that comes has a dependency on n. So, let me prove these relations. So, A psi n is equal to 1 by root n A dagger psi n minus 1. So, I am proving the second one first, because psi n plus 1. So, A psi n is A, now the psi n I am generating from n minus 1 by operating it by a square, I mean with a dagger, okay, A dagger. A dagger acting on psi n minus 1, and then of course, will give me a psi n and with this normalization that you have 1 by root n. So, we have this A psi n which is equal to that. So, this is equal to 1 by root over of n A dagger A plus 1, this is a psi n minus 1. Okay, so, this is equal to 1 by root over of n, 1 by root over of n, and you have this as A dagger A, which is an eigenstate of psi n or psi n minus 1 plus psi n minus 1, and so this gives you 1 by root n, and then there is a n minus 1 psi n minus 1 and plus, so there is a psi n minus 1. So, we have plus 1 and then there is a psi n minus 1, okay, there. So, this is equal to a root over n psi n minus 1, which is what we have claimed. So, A acting on psi n gives you a different state and returns you a coefficient which is root over n, but changes the state, and it is definitely not an eigenstate of psi n, or rather psi n is not an eigenstate of A. Similarly, we can show the other relation, that is A dagger. Okay. I just leave it to you to do it, but it is the same thing. You take a dagger of psi n, and then these A dagger you can, I mean the psi n, you can write it in terms of n and so on, or if you want it, I mean we can do it in just 1 or 2 lines. So, we have these adjoint equations of these ones that we have done is psi n A is equal to root over of n plus 1 psi n plus 1, and psi n of A dagger is equal to root over of n psi n minus 1. And so, basically A decreases, you can again show that what we have written here is that A dagger acting on psi n is equal to root over n plus 1 and psi n plus 1. Okay. That's coming from the top expression that you have. And finally, so we have these x, are these x and p, do they have the psi n as eigenfunctions? And it does not look like, because since A and A dagger, their eigenfunctions psi n's are not eigenfunctions of them. So, x and p will also not have psi n's as the eigenfunctions, but let us see that. So, x psi n is, now we have gone back to the original x operator, which is h cross over m omega, and then there is a 1 by root 2. So, you can combine the root 2 here itself. So, it is H cross by 2 m omega, and it is a dagger plus a psi n. Now, it is very clear that for x and p also we are not talking about these eigenfunctions. I mean, the psi n's are not eigenfunctions of x and p either. So, but H is formed of x and p, but luckily H is formed of n plus half. So, the psi n's are eigenfunctions of n, and hence they would be eigenfunctions of x. So, p and x are combined in such a manner that even though x and p do not have eigenfunctions of psi n, but H has eigenfunctions, psi n as a eigenfunctions. So, this is equal to H cross by 2 m omega, and then we have this a dagger acting on this will give n plus 1. By the way, in some books you will have psi n written as n, just n ket, but it means the same thing. So, psi n plus 1 and plus root over of n psi n minus 1, and so these are that, and so basically so p psi of n is equal to I m omega h cross by 2, and this you can show that it is equal to n plus half psi n plus 1 minus root over n psi n minus 1. So, in the same spirit that psi n is not an eigenfunction of x, it is not an eigenfunction of p as well. Okay. And one last thing that I want to show you is that what are the matrix representations for A and A dagger. Okay, so we have these relations, that is psi n prime, this which is some state which is different than n maybe. So, in this particular case it is definitely this is different than n. So, it is root over n delta n prime n minus 1, and similarly for the psi n prime A dagger psi n, this is equal to root over n plus 1 delta n. So, this n prime n plus 1. Okay. So, what is the matrix representation for A? So, A matrix representation, and now this is say written like this. So, this way you have n running this way and n prime running this way. Okay. So, it is the matrix elements are root over n into n root over n, but its connecting states which are n prime will be n minus 1. So, you have all the diagonal elements to be equal to 0, and the off diagonal elements are like root over 1 here, root over 2 here, and root over 3 here, and so on. Okay. And there has been nothing. So, there is 0 here, there is a 0 here, and the only non-zero will be like this. So, it is in this n prime basis, because your relationship is so you have a n prime. Now, I am writing it psi n prime as n prime A n, this is equal to root over n delta n prime n minus 1, which means if n prime is equal to n minus 1. So, if n prime is say 1, then n has to be 2. So, that is why this way n runs and this way n prime runs. So, the 1 2 element survives, which has a value root over 1, and similarly this 2 3 element survives, which has a value root over 2, and so on. And because there is nothing in the diagonal element, it is very clear that these are psi n's are not the eigenstates of A and A dagger. So, similarly we can write it for A dagger as well, and then we again have 0 0 0 0 and so on, and then we now have a root over 1 here, and a root over 2 here and so on, because this relation is again n prime is equal to n plus 1. So, you have a 1 to kind of, I mean, so this will have n prime a dagger n is equal to root over n plus 1, and we have a delta n prime n plus 1. So, if n prime equal to 2, then n is equal to 1. So, you have this 2 1 element and 3 2 element, etc. They survive. Okay. So, these are the matrix representations, and at least if we do the the ground state wave function and the first excited state wave function, at least have a form for them, that will make the story complete, because you have been able to picturize it as these various energy levels of the harmonic oscillator. They are occupied by the number of oscillators corresponding to, which is exactly the same as the quantum number that is associated with it, namely the n. Okay. So, let us at least do one or two wave functions. So, let us start with the ground state wave function and try to get an idea that what is, and so we start with a psi 0 equal to 0, which is known, because you can't do any more destruction of particles or annihilation of particles. There is no particle at all, and we take this in the original operator. Now, we need this original operators x and p, because we need all these m, omega, etc. there present, so that you can have a one-to-one correspondence with what you have learned through this algebraic method. So, this is equal to x and plus I divided by root over m omega h cross p, and that acting on psi 0 yields a 0. What I have done is that I have written a in terms of x and p, which is what you see here. We have written somewhere x and p in terms of, so we have written that at the beginning, where we have written a and a dagger in terms of x and p, and also the inverse relation, that is x and p in terms of a and a dagger. So, here we are using that, we are writing a in terms of x and p. So, we will write p as minus I h cross d dx or del del x. So, if you do that, then what we have is that m omega by h cross x plus d dx, that is equal to and we have this psi 0 x. So, it is in the coordinate space, and this is equal to 0. So, if you solve this, you have a derivative of x. So, what you do is that you bring this x down. So, it is like a psi 0 prime divided psi 0 prime x, which is d dx of psi 0 x divided by and so this d psi dx, and then there is a psi. So, we have a psi 0 prime and a psi 0 x, and this, if you solve, what you get is that the psi 0 x is equal to some constant exponential minus m omega by 2 h cross x square. This is very comforting, because indeed the lowest eigenstate or the ground state wave function of an oscillator is simply a Gaussian, which we have seen earlier, that this is the, so it's basically that ground state, which is a Gaussian. You have to draw it a little carefully. Okay. So, that is the ground state we got by this method. Okay. And you can get the first excited state as well, and by operating it on this a dagger, and then multiply it by. So, I sort of left these one or two steps here, but it can be filled in by you easily. So, now this normalization constant has to be found out, and this normalization constant can be found out by by taking this equal to 1 and 1, and this thing comes out as m omega by pi h cross whole to the power 1/4. So, what you do is that you take a c square exponential minus m omega by 2 h cross. So, it becomes h cross x squared dx, and write down this integral as exponential minus alpha x square from minus infinity to plus infinity is nothing but root over pi by alpha. This is called as a Gaussian integral. So, using this Gaussian integral you can do that. And now, once you have done or rather found this ground state wave function, all the other eigenstates of the oscillator can be generated. And how you do that is the following, that you can write down this psi n of x, which is a 1 by root over n factorial, and you can write it as psi 0 x, or rather this is in the coordinate space. So, this is like a dagger whole to the power n and a psi 0 x. Okay. So, do it for n equal to 1 and you will get this state, that is a psi 1 and so on and so forth. And once you do everything and then do a normalization of that as well, what you get is that 2 to the power n factorial, it is h cross by m omega whole to the power n, and this whole to the power half m omega by pi h cross and whole to the power 1/4, and we have this exponential function. Okay, so this is that a dagger, which can be now written as m omega by h cross x minus dt x whole to the power n, and we have this ground state which is minus m omega by 2 h cross x square, and you can really get all these things. So, just a few lowest eigenfunctions. So, psi 1 is if you do it once, then it comes out as 4 over pi and m omega by h cross whole cube, this whole to the power 1/4, and x exponential minus m omega by 2 h cross x square, and so on and so forth. So, psi 2 x is equal to, this is equal to m omega by 4 pi h cross whole to the power 1/4, and we have this 2 m omega by h cross x square minus 1 e to the power minus m omega by 2 h x square. So, this is the Harmonic polynomial h 1, this is the Harmonic polynomial h 2, and so on. Okay. So, you can actually generate all of them, and in terms of these like whatever we have seen it there, and so these will give you entire spectrum as well as the eigenfunctions of that. Okay. Now, one last thing and quick thing that we want to do here is we want to talk about the degeneracy of these oscillators. Now, the oscillators, of course, they do not have, in 1D there is no degeneracy. So, let us see that in 3D what kind of degeneracies do we get. So, what we have is that the energy is given by n plus 3/2 h cross omega, and this is equal to nx plus half plus ny plus half plus nz plus half. So, in each direction we have this. So, it is nx plus ny plus nz plus 3/2. So, which means that nx plus ny plus nz is equal to 3/2. Okay. So, the degree of degeneracy will have to obey this. I am so sorry, this is equal to n, not 3/2. So, this is equal to n. So, that is why, so the 3/2 comes from these 3 halves. Okay. So, let us first choose nx to have any of these values. 0, 1, 2 and this n, right. I mean it can go all the way up to n. In that case your ny and nz, for the last value that you see here, your ny and nz will be equal to 0. So, we have ny plus nz, that is equal to n minus nx. Okay. So, what are the different possibilities for ny nz? So, this ny nz pair have possibilities as n minus nx plus 1. How this is coming? It will be 0, n minus nx, that is for when nx is equal to 0. So, this is 1, then it is 1 n minus nx minus 1, then it is 2 n minus nx minus 2 and so on, and this will be the final one will be n minus nx and 0. Okay. So, these are the possibilities for this ny and nz, and these if you count they are n minus nx plus 1 because it started from 0. So, the degeneracy can be now calculated. So, degeneracy let us call it as Gn. So, Gn is equal to nx equal to 0 to n n minus nx plus 1, that is the pair n ny nz can take all these values and where nx will go from 0 to n. So, if you do this simplification, so this becomes n plus 1 and sum over nx equal to 0 to n and sum over 1, that is the last term, and last term is n plus 1 term. So, the first term and the last term. So, this is n plus 1 and then you have a sum over 1, and now you have n x equal to again 0 to n, sum of n natural numbers, but now there are n plus 1 of them. So, this is n plus 1 into n plus 1, you sum 1 for n plus 1 times. So, it is n plus 1 into n plus 1 minus this is n which is n plus 1 times. So, it is n into n plus 1 by 2, and so this is equal to n plus 1 whole square, and this is n into n plus 1 by 2, and if you do a simplification of that it becomes equal to. So, if you take a n plus 1 common, so you have a n plus 1 minus n by 2. So, this will become equal to n plus 1 and 2 n plus 2 minus n divided by 2. So, this is equal to n, this is equal to what, n plus 2. So, it is n plus 1 into n plus 2 divided by 2. Okay. So, the ground state is of course degenerate and so on. So, so for n which is nx plus ny plus nz. So, suppose n equal to 3 is how many fold degenerate. So, degeneracy of that is equal to 3 plus 1 into 3 plus 2 divided by 2. So, that is like 4 into 5 divided by 2. So, that is like 10 fold degenerate. Okay. So, the harmonic oscillator in higher dimension, now we have shown it for 3 dimension, has a degeneracy which goes as n into n plus 1, n plus 1 into n plus 2 divided by 2. And so, each of these energy levels which was non-degenerate in 1D, in 3D they become degenerate, which the degeneracy is for a given n, we have found it out equal to 10 fold. So, that completes the discussion of this harmonic oscillator. We have done both this algebraic method of solution, and then we also have figured out a solution using this A and A dagger operator. They are all very neat. One does not have to go through a very rigorous mathematics, but just by looking at the properties of these A and A dagger, which are called as raising and lowering, but more sort of conveniently, or rather more more usually or more frequently, they are called as the creation and the destruction operators or annihilation operators. creation and annihilation operators. Sometimes it's called as creation and destruction operators, and this gives you the complete description of the problem without resorting to the algebraic method that we have seen earlier. So, I will stop here for today. Thank you.